Find an exponential function or linear function that models the data. So we have two sets of data here for our examples. One of them is linear and one of them is exponential, and it's pretty obvious which one is linear and which one is exponential. Here you can see that the y values are decreasing at a constant rate, and they're going down by 4. And then the x values are increasing by a constant rate of 1. So to go from -3 to -2, you add 1, -2 to -1, you add 1, and so on and forth. So the change is constant, you just add 1, and here you subtract 4. That's obviously linear. So when we're, let's start with the linear, since we're most familiar with that. The function that models a linear data is going to be f of x equals mx plus b. So to find the actual function, we just need m and b. And m, as I alluded to earlier, is the rise over the run. And here the run is +1. And the rise, which is actually a decline or a fall, is -4. The negative indicates that you're going down. So the rise over the run, our m, is -4 over 1, which is -4. And our b is the value of y when x equals 0. So here our data, we have x equals 0. So our b value is 16,372. 16,372. So if we're looking for a function here, one that works really well for this is f of x equals -4x plus 16,372. So there's our linear function that models this data. Now, this is obviously exponential because you can see these y values are rising rapidly. You start at a 0.625 and just a few places over, you're at 160, whereas the x values are constantly, you're adding 2 each time. So let's go ahead and find the model for this exponential function. And remember, an exponential function, just like linear has a general form for a linear function, we have f of x equals c a to the power of x. This is an exponential function because the variable is in the exponent, and we require that a is greater than 0. Now, we need to just find c and a. Just like we found m and b for our linear model, we're finding c and a for our exponential. So when you plug in x equals 0, you have a to the 0 power. That's just 1, no matter what a is. So we're going to do that first. We're going to plug in, we have f of 0 equals c a to the 0 power. And a to the 0 is just 1. So c times 1 is just c. So c is equal to f of 0. And what is f of 0? That is just 10. So c is equal to 10. We found our c. And now we're going to find a. So we need to take another point in our data. It would be nice if we could just plug in a 1 there, but we're not given the y value for 1. So we'll just go with 2. And we already know c is 10. So now we have f of x, but not, in this case, 2. F of 2 is 10. That's our c. We don't know a yet. We're just plugging in a 2 into our model. We know c is 10. We're plugging in a 2, and now we can solve for a. First of all, what is f of 2? Well, that's just 40. So we have that 40 is equal to 10 times a squared. And now I'm going to go ahead and divide both sides by 10. And that gives me 4 equals a squared. This is a quadratic equation, and I can use, I'm kind of running off the screen here, let me. I can use the square root property and take the square root of both sides, and then I get A is equal to 2. Now, normally I would say A equals plus or minus 2, but I know that A has to be positive, right? So I'm not even gonna bother looking at -2 because I know A can't be -2. So now we found C is 10 and A is 2. And so the specific model that we have here for this function, I'm running out of room to write it. I'll just write it right here. Let me write it in a different color. Is going to be f of x equals 10 times 2 to the x. And so this is our exponential model for this set of data.